Okay, so now secant and cosecant. So first things first, we're going to start off with secant. But let's look at how we solved tangent and cotangent. Remember, we found tangent and then used the reciprocal, since cotangent is the reciprocal of tangent. We use the reciprocal to graph cotangent. Well, the same thing occurs here. Okay, if I were you, the very first thing I would do when I get secant, we know that secant is 1 over sine. So the very first thing that I would do is I would take my graph of sine and I would draw it first. I'm serious. On every one of these, I would draw, and that should be a positive, by the way. I don't know why I wrote negative. On every one of these graphs, I would draw our original function. So and until you're told to do it for a certain length, I'm going to just do it for 2 periods just so you see the full effect of it. So that's why I'm doing what you see here. This will give us 2 full periods, because remember, the period of sine is 2 pi. Now, here is our graph of sine of x. If you remember from before, sine starts at 0, goes up, down, and back up to 2 pi. And it does a similar fashion going in the other direction. So this would be the graph of sine, the largest number of sine being 1, the lowest number being -1. I know I'm a little off on my graph, a little bit of a human error with this pen, okay? So this is our graph of sine. Now here's the important thing for you to remember. Because cosecant, which we're now going to try to graph, because cosecant is a reciprocal of sine, that means anywhere we have an x-intercept is now going to be a vertical asymptote of cosecant. So there's going to be a vertical asymptote here, here, and here, all the way across. So simply because they were x asymptotes in sine, because cosecant's a reciprocal, it makes them vertical asymptotes now. They go from x-intercepts to vertical asymptotes. So we got some very important information here. We know the vertical asymptotes occur at k pi, functions of pi. So notice there's multiples of pi. So we have multiples of pi all have vertical asymptotes. Now, how are we going to draw cosecant? Well, believe it or not, I have students that think, well, if you can draw the sine and cosine functions, this is going to be a piece of cake for you. Because watch how we're going to do this, okay? And here's how. Notice right here. That is a maximum point for sine. Well, if it's a maximum point at sine, when we do the reciprocal, that means it's going to be a minimum point at cosecant. So that means our graph, if this is a minimum point, that means it's going to rise this way and rise this way, since it's a minimum point down of our cosecant. Now notice, this is a minimum point on sine. When we flip it for cosecant, because we're doing the inverse, remember, when we flip it for cosecant, it's going to make it a maximum point of cosecant, which means it has to be at the top of the hill. Okay? This is a minimum point of cosecant, so we have to draw it like this. And this would be a maximum point of cosecant, so it must be drawn like this. Now here's what I want you to realize. Even though we have these vertical asymptotes, the period is still, excuse me, still 2 pi. Okay, how do you get that, Mr. Francis? Because a moment ago you told us with tangent and cotangent. Excuse me again. Sorry about that. With tangent and cotangent, I told you to look between the asymptotes. Well, you got to look at the graph sometimes, because look at this graph here. Notice the whole purpose of a period is it repeats itself, right? You're repeating what's happening in that period. So notice we go through this whole thing here before we repeat again. Then we go through the whole thing one more time. So the period here is actually from 0 to 2 pi, from negative 2 pi to 0. So our period is actually the length of 2 pi. Okay, that would be the period for this particular function. Excuse me. That would be the period for this particular function, would be 2 pi. It's where the graph is repeating itself. That's what you got to look at more than the asymptotes, is where is it repeating? Where is it repeating? So, very similarly, we can get secant. Okay? So, if we are looking for secant now, remember secant is the reciprocal of cosine. So the first thing I would do, that should be a positive one. The first thing I would do is I would draw my, this should be pi, I would draw my cosine graph, since we're looking for secant. Okay, and again I'm going to extend it both directions, just like we did with sine. Alright, so let's draw cosine on the same graph that we're going to draw secant. So if you remember, cosine started up here at 1, and we went through like this. So it would look like this. This would be our cosine graph. So in much the same fashion, everywhere there's an x-intercept with cosine is going to be a vertical asymptote with secant. So I've got a vertical asymptote here, 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 and here. Now what is the general equation of that vertical asymptote? Well, it's pi over 2 plus any pi multiple of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Okay, so that would be our vertical asymptotes. Now, we're going to draw our secant graph in much the same way. Now notice here, this is a maximum of our cosine graph, so it's going to be a minimum for secant. So if it's a minimum, it's got to be at the bottom of the hill, so we draw it up like this. Here, it's going to be a maximum for our secant graph, so it needs to be at the top, right? And remember, as we get closer to the vertical asymptotes, we start going toward infinity or negative infinity. So, for instance, with this is a minimum for secant, and as we get close to these two, we're going to positive infinity. So that's another way to look at it instead of the bottom of the hill reference I've been doing. That's a layman's term point of it, but if you look at it in terms of the mathematical perception, as we get closer to the vertical asymptotes, where you get closer to infinity or closer to negative infinity, which is why our graphs they look like this U shape. Okay, that is why they look like this U shape. Okay, so this is a minimum for cosine, so it's going to be a maximum for secant. And as we go to the left, we get closer to the line, to the vertical asymptote. Same thing with the right. And finally, this is a minimum for secant. As we get closer to the vertical asymptote, we're going toward infinity. So this is what our graph of y equals secant looks like. All right, so again, I'm going to ask you this time, what is the period? Where does our graph begin repeating? So if you look here to here is one period. Now if you continued on with this, it would look like this, okay? If you were to continue on with this graph. So see how we begin to repeat the values over again? Now notice, this is pi and another distance of pi. So our total period is going to be the same as cosecant, which is 2 pi. The total period is going to be 2 pi. Okay, so I hope this helps you. These graphs are on page 131 in your book. I hope this helps you understand the graphs of secant and cosecant. So we'll have one more video. Now you're going to see a lot of things in your book about making T-charts, and that's fine. If you want to make the T-charts like your book does, by all means do it. I recommend you reading this chapter. It's a good chapter to read. You're going to see a lot of things in your book about using graphing calculators. I don't recommend that. Check your work, by all means, check your work with the graphing calculator. But here's the problem. I'm going to make you graph it like you see it here on this page on an exam. So you better be developing that skill of how to graph these by hand, okay? Keep that in mind whenever you see all these graphing calculator things. And I'll have to let you use the graphing calculator on your quiz at home, because it's one of those things where the problems in the book say a lot of graphing calculator stuff. But I'm going to want you to know this by hand, okay? So we have one more video on max and min, and then we'll be done with this particular section.